Ladies and gentlemen, in this short video, we're going to look at how to solve problems using conservation of energy equation. So for this example, I have a cart at rest against a coiled spring on a frictionless track. The spring pushes on the cart, adding 150 units of energy, joules of energy, into the system as shown. The system is going to consist of the cart, the earth, and the track only, and we're not going to have any air resistance. So we won't have any friction, we won't have any air resistance, we won't have any energy lost to dissipated energy in this problem. The first thing that we have to do to solve this problem is to identify where do we want to put our zero height for gravitational potential energy. I would suggest that we put it at the very bottom of the track so that at points A and B, the height of the cart is 0, so there won't be any gravitational potential energy. With the earth and cart in the system, I know that I'm allowed to include gravitational potential energy, but since my cart at position A is at my ground level, my H equals 0 level, then I won't have to worry about any gravitational energy. So you can see I put it at 0 units of gravitational energy at the beginning. Since the cart is at rest, it will also have 0 kinetic energy. And since the spring is outside the system, my system does not have any elastic energy. If the spring were inside the system, then I would have elastic energy. But since the spring is outside the system, I do not have any elastic energy at position A. And I also don't have any dissipated energy at position A. So at position A, the energy of the system is 0. I have no energy. But at position B, the cart is absolutely moving. It's going to have some kinetic energy, and the system gained that energy because it said the spring was working to put energy into the system. So if I were to fill out my system flow diagram, so in looking at our energy flow diagram, the LOL diagram, at position A, my system has 0 energy. At position B, I have 6 blocks of kinetic energy, and that energy came from the spring. The spring was working to put energy in. So you can see the spring, which was outside the system, put 6 units of energy into the system, and it showed up in the form of kinetic energy. So with that, I'm able to write my energy equation, and our qualitative equation would be that the working energy added by the spring is equal to the kinetic energy at point B. So with that, I'm able to find the velocity of the cart at point B. Let's look at how we do that. We know that the spring added 150 joules of energy. So 150 joules of energy added by the spring has to all go into the kinetic energy column for the cart. And the kinetic energy is equal to 1/2 mv squared. Substituting in the mass and the velocity of the cart, we know that the cart is 250 grams. I'm not allowed to use that, so I have to convert that to kilograms. So that'd be 0.25 kilograms. And then we simply rearrange this algebraic equation to solve for V. And we see that the cart is moving with a velocity of 34.6 meters per second. In part B of this problem, they want us to determine the speed of the cart at the top of the loop. So they give me the radius of the loop is 75 centimeters, and they want to know how fast it's going. So my position B diagram hasn't changed. The cart's still moving with the same kinetic energy that it had before, 150 units. Now at position C, though, the cart is up off of the ground a little bit, so it has some gravitational energy, and it's still moving, so it has kinetic energy. But since most of that energy is in the gravitational column, I expect less to be in the kinetic column, which is why I broke it up into 4 blocks and 2. When writing my qualitative energy equation, I would see that the kinetic energy at B, which we know is 150 units, has to equal the kinetic energy at C plus the gravitational potential energy at C. And now we can go ahead and solve for the amount of each energy column in our equation. And putting that in our equation form that we saw in the other videos, the kinetic energy is 1/2 mv squared, and the gravitational potential energy is mgh. So let's solve for the amount of gravitational potential energy first. Knowing that the radius was 75 centimeters, the total height would be the diameter, or twice of the radius. Plugging in our values, we see that the gravitational energy is 3.7 joules. So actually not very much of our 150 is used in our gravitational column, but that's okay. So now we can solve for the amount of kinetic energy. And we see that the cart has 146.3 joules of kinetic energy, which finally allows for me to solve this algebraic equation to find the speed of the cart at the top of the ramp. And we find that the cart has a speed of 34.2 meters per second at the top of the ramp.